In the last class, I have clearly explained about Biot-Savart's law, in which we have found magnetic field intensity at a given point. In the today's class, we will see about Amperes circuit law. The statement is Amperes circuit law and Maxwell's equation. The statement is integration of magnetic field intensity along a closed path is equal to the current enclosed by that closed path. And we will integrate magnetic field intensity with respect to differential length. That is, closed path is indicated by this circle H dot dl. That is, integration of this magnetic field intensity with respect to differential length is equal to current enclosed by that closed path. I will show you how to find out the direction of that closed path also by using the right hand thumb rule. Both are vectors. So this is equation number 1. By Stokes theorem, integral H dot dl is equal to integral del cross H dot ds. This will be equation number 2. But I have already discussed about, clearly explained about, that is current density J into ds is equal to current. So we can apply this formula for finding the current enclosed by the closed path. Let this be equation number 3. Okay, comparing these integrals with respect to differential surfaces, we will get del cross H is equal to J. Okay. This is Maxwell's third equation. In differential form. Since J is not equal to 0, this is not conservative. Now we will see about the applications of this Amperes circuit law for line current, infinite line current, and infinite long sheet of current, and infinitely long coaxial transmission line. We will see about these 3 applications. So we should understand this formula. That is H dot dl is equal to current enclosed. In the Gauss law we have seen, that is integral d dot ds. That is flux density is integrated with respect to surface, with respect to differential surface, which is equal to charge enclosed. Okay. Here we are considering the current now. That is H dot dl is equal to current enclosed by the closed path. Here is current enclosed by the closed surface. And by Stokes theorem in Gauss law, we have seen this integral d dot ds is equal to del cross d dot dv. Okay, and the charge enclosed is rho v dv. This is charge enclosed by the closed surface. This is the charge enclosed. Okay, these are the similarities between Gauss law and Amperes circuit law. Now we will see about finding magnetic field intensity for infinitely long wire, which is carrying current I. We will find out the magnetic field intensity for a infinitely long wire. So applications, three applications are there. That is finding magnetic field density for a infinitely long wire. First one, infinitely long wire. Means the current will be flowing in that infinitely long wire. We need to find out the magnetic field intensity for this infinitely long wire. And second one is infinitely long sheet current. Sheet current means in the infinite long sheet, current will be flowing in that. For that, we will find out magnetic field intensity. And third one is infinitely long coaxial transmission line. Infinitely long coaxial transmission line. Transmission line. In today's session, we'll see about first and second. In the next session, I will clearly discuss about infinitely long coaxial transmission line. There is magnetic field density due to flow of current in the infinitely long coaxial transmission line. Today, now I will discuss about this. We'll see about infinitely long wire. Infinitely long wire. Y, X, Z. Current is flowing like this in the infinitely long wire. This is negative Z axis. Current is flowing like this. The Amperian path, that is the direction of the magnetic field lines, will be shown by the right hand thumb rule. This is the conductor, that is infinite long wire, and the curled fingers show the direction of the Amperian path, that is the direction of the magnetic field lines. So these can be moved like this. Current is flowing upward, the magnetic field lines will be moving like this. Okay. H and DL. This is the Amperian path. Amperian path. Let this be DL. DL and H are in the same direction, whereas the Z is perpendicular to this circle. So it is perpendicular to Z, DL also, and rho. Rho is the radius of this Amperian path. This is DL. I consider small length of this Amperian path, and this is d phi. The cylindrical coordinates are rho, phi, and z. Rho is the radius of the circle, and phi is the angle between the radius of the circle and the x-axis. Okay, and z is the z coordinate. This is same as the Cartesian coordinate. Okay. Infinite long way I have considered, and I have considered the Amperian path. Now let us find out this integral h dot dl. H dot dl is equal to I enclosed. H dot dl is equal to I enclosed. So I enclosed is nothing but current I. What is H dot dl? Okay. H is tangential. Direction is the direction of, that is H is in the direction of A phi cap. Okay. I have already covered that differential length in cylindrical coordinates is dr ar cap plus rho into d phi a phi cap plus dz into az cap. These are the differential lengths. Okay. This is in the direction of AR, this is in the direction of A5, this is in the direction of AZ. Okay. So H into A5 cap. So tangentially the direction of this unit vector for the coordinate phi is tangential to the ambient path, and dl is also in the same direction. Okay, and h is also in the same direction. H direction is a5 cap, h into a5 cap dot dl. What is dl here? dl is rho into d5 into a5 cap, which is equal to current I. So h is constant here, h and rho into d5 a5 cap dot a5 cap, which is equal to a5 cap is magnitude is 1, so both are the same direction, so angle is 0, so cos 0 is 1, so we can write it as h integral rho is also constant and d5 from 0 to 2 pi. So h rho, if we integrate this, we will get 5 0 to 2 pi, which is equal to I. So h into rho into 2 pi is equal to I. So h is equal to I by 2 pi rho A5 cap. A5 cap. Okay, this is magnetic field intensity for infinitely long wire carrying current I. Next we will see about the infinitely long sheet of current. This I will find out the magnetic field density for a infinitely long sheet of wire carrying current. So what are the units of this H? Ampere per meter. Ampere per meter are the units of this magnetic field intensity. We will see about second one, that infinitely long sheet current. That means infinitely long sheet carrying current I. Y, Z, and X. The long sheet which is carrying current I. So when the current is flowing in the direction of y axis, so the magnetic field lines will be perpendicular. The circle which is found by this magnetic field lines will be perpendicular to this current I. That means it encloses the current I. So I will show it by a rectangular path. Path direction is shown by the right hand thumb rule. the current is flowing in the direction of Y, let it be K. K is the current density, amperes per meter. This K is surface current density divided by K. Okay, K is equal to vector K is equal to K into AY cap, since it is in the direction of Y axis. And the ambient path direction is shown by right hand thumb rule. Okay, shown by the curved fingers. So it should be like this. Let this distance be D and let this be A. Okay, length be D and width be A. This is the Amperian path. Amperian path. We will find out the magnetic field intensity due to the current flowing through this path. Okay, that current density is given by K, which is equal to K into AY cap, amperes per meter. Amperes per meter. So integral H dot dl is equal to, what is the current enclosed? Current enclosed is K into AY cap. K into AY cap. The current flowing through this Amperian path is into D. So which is equal to KD amperes. K into D. The total current flowing through this Amperian path is K is the magnitude of this current vector K. So K into D, that is that much current will be flowing through this Amperian path. So which is equal to K into D. Now D, let us write B. B is the breadth, let us say, and I is the height, and B. K into B. K into B amperes. Amperes. Okay, let us find out this H dot dl for this Amperian path. Let the path be 1 to 2, 2 to 3, 3 to 4. Okay, let us consider the path 1 to 2 now. This H dot dl is equal to integral from 1 to 2 H dot dl plus integral from 2 to 3 H dot dl plus integral from 3 to 4, 1 to 2, 2 to 3, 2 to 3, 3 to 4 H dot dl plus integral 4 to 1 H dot dl. H dot dl. So from 1 to 2, that is Hz. H will be along the path 1 to 2, 2 to 3, 3 to 4, 4 to 1. So what is H in the path 1 to 2? That is downward, so it is minus Hz. So 1 to 2 it is equal to minus Hz into minus Hz into minus A. Minus Hz into minus A plus H dot in 2 to 3. 2 to 3 it is X is negative. So Hx is negative into B is also negative, minus B. 3 to 4, Z is positive, so that is Hz into A. Hz into A. Hz into A. 4 to 1, 4 to 1, the direction of X axis, Hx, and B is also positive. Hx into B. So 1, 1 to 2, 2 to 3, 3 to 4, 4 to 1. Okay. So finally we should prove that only the x components will remain. Okay, and this will get cancelled. But actually it is HZA, HZA. It should be equal to 2 HZA. But I'll show you how it is cancelled. So when the current is flowing like this, current is flowing in the sheet. Let us consider two components, I and I. So by right hand thumb rule, the ambient path, that is magnetic field direction, will be like this. Okay, magnetic field direction will be like this. So it is moving up, it is moving down. Then I will show you how these components will get cancelled. Z components will get cancelled by finding the by drawing the rectangular paths. This is current I, this is current I. Rectangular path for this I. This is the rectangular path for this I, and for this current, the rectangular path. So this is Hx, 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 and this is Hz, and this is Hx, this is minus Hx, and this one is minus Hz, minus Hz. For this path, Hz, and this is minus Hz, Hx is negative, Hx for this path is positive. For this path, this is minus Hx, and this is H plus Hz, here it is minus Hz, and this one is Hx, and this one is minus Hz. So this minus Hz, this plus Hz components will get cancelled. So only the x components will remain. So this one and this one will go off. We'll get 2Hx B. That is H is equal to 2Hx B. 2Hx B, which is equal to Kb. Kb is the current which is enclosed by the path or the rectangular path. B and this B will get cancelled. So Hx is equal to K by 2. Hx is equal to K by 2. Hx is equal to K by 2. Okay. When Z is positive, H is equal to K into Ax cap, when Z is greater than 0, and it is equal to minus K Ax cap when Z is less than 0. When Z is less than 0. Z is less than 0. So consider this line current density in the direction of y-axis. It can be in the direction of z or x-axis also. Let us find out the direction of this H. The K is equal to vector K is equal to K into A y cap, since it is in the direction of y axis. Let us multiply, let us find out the cross product of these two on LHS and RHS. Ax cap is equal to k into ay cap cross ax cap. K cross az cap is equal to k into ay cap cross az cap. So k cross az cap is equal to, what is ay cap cross az cap? Ax, ay, az, ax cap cross ay cap is equal to az cap, and ay cap cross az cap is ax cap. So it is ax cap. So it is ax cap. So in general, this k cross an cap is equal to k into ax cap. Okay, z is normal to ax. Since it is in the direction of y axis, we got az cap. So it can be any other axis. So I have written k cross an cap is equal to k into ax cap. So this k into ax cap can be written as h is equal to k cross an cap amperes per meter. For infinitely long sheet current, the magnetic field intensity is equal to k cross an cap. Okay, in the next session, I will discuss about the third application.